Our program goal is to provide you with a basic understanding of incineration techniques used in air pollution control and a look at various incinerator devices. We will cover what is incineration and what are incinerators, types of incinerators and their designs and components, proper operating conditions, causes of decreased performance, and performance monitoring. In vapor incineration processes, organic contaminants are removed from a gas stream by oxidizing them to other compounds. If the organic compounds are composed of carbon and hydrogen, then the products of that oxidation are carbon dioxide and water vapor. However, if the organic materials contain chlorine, fluorine, or sulfur, then hydrochloric acid vapor, hydrofluoric acid vapor, sulfur dioxide, or other compounds may be formed. In general, incinerators are capable of destruction efficiencies greater than 95%. Some incinerator designs have destruction efficiencies greater than 99%. There are three common types of incineration processes: flares, thermal oxidizers, and catalytic oxidizers. Flares are usually used for gas streams that have organic vapor concentration greater than 2 to 3 times the lower explosive limit. If the waste gases do not have sufficient heat content, fuel will be added to the gas stream. This is referred to as a fired or endothermic flare. A typical flare consists of a system that first collects the waste gases, then passes them through a knockout drum to remove any liquids before entering the flare stack. Flame arrestors are placed between the knockout drum and the flare stack to prevent flashback of flames into the collection system. The flare stack is a hollow pipe that may extend to heights above 150 feet. The flare tip is at the top of the stack, where the waste gases are ignited by pilot flames. The flare tip is designed to provide good mixing characteristics over a range of waste gas flow rates, while maintaining smokeless combustion. Steam jets are one of the most effective ways to mix air with the waste gases. The steam also reduces polymerization of organic compounds in the waste gas stream and reacts with the gases to produce oxygenated compounds that burn at lower temperatures. In order to reduce the noise, light, and safety concerns inherent with an open flame, the flare may be located at ground level. Ground flares consist of multiple burners enclosed in a refractory lined shell. The waste gases are introduced through a jet or venturi to provide turbulent mixing, and the combusted gases are discharged through a stack. Some plants incorporate both designs, a ground flare for normal operation and an elevated flare for emergency releases. Thermal oxidizers are used for contaminated gas streams that have an organic vapor concentration that is generally less than 50% of the lower explosive limit and usually less than 25%. The thermal oxidizer consists of a refractory brick-lined chamber that has one or more gas or oil-fired burners located at one end. The burners are used to heat the gas stream to the necessary temperature to oxidize the organic contaminants, typically 1,300 to 1,800 degrees Fahrenheit. The contaminated gas stream does not usually pass through the burner itself, unless a portion of the gas stream is used to provide the oxygen needed to support combustion of the fuel. The combustion chamber is sized to provide sufficient residence time to complete the oxidation reactions. Typical residence times are 0.3 to 0.5 seconds, but may be longer than 1 second. The time needed for destruction depends on the temperature and the mixing within the chamber. An alternative to installing a thermal oxidizer is to incinerate the contaminated gas stream in a process heater or boiler. This avoids the capital cost of new equipment. The contaminated gas stream is typically injected close to the main burners or may be used as part of the combustion air supplied to the burners. Process heaters and boilers are normally designed to operate with combustion chamber temperatures greater than 1,800 degrees Fahrenheit and with flue gas residence times in excess of 1 to 2 seconds. These conditions are similar to those of conventional thermal oxidizers. There are some limitations in the use of a process heater or boiler as an incinerator. The boiler must operate within about 40 to 100% of the design load in order to have the necessary temperatures for organic vapor destruction. The waste gas stream should be only a small portion of the total gas flow through the unit. If the volume of additional gas is large, maximum recommended velocities through the unit would be exceeded, potentially lowering the destruction efficiency of the system. Finally, there should be nothing in the waste gas stream or its combustion products that would present a corrosion problem or cause deposits on heat transfer surfaces. Catalytic oxidizers are used for contaminated gas streams that have an organic vapor concentration that is less than 25% of the lower explosive limit. Concentrations greater than this cause high temperatures that can damage the catalyst material. A catalyst is a substance that accelerates a chemical reaction without undergoing a change itself. The typical catalysts used in incineration are noble metal oxides of platinum, palladium, or rhodium that are deposited as a thin layer on a high surface area support material. Base metal oxides such as vanadium pentaoxide, titanium dioxide, or manganese dioxide may also be used. In catalytic oxidation, the contaminated gas stream is heated to the required temperature by a gas-fired burner and then passed through the catalyst material referred to as the bed. The catalyst causes the oxidation reaction to occur at much lower temperatures than would be required for thermal oxidation. The typical catalytic oxidizer operates at 600 to 850 degrees Fahrenheit. This is the principal advantage of catalytic oxidation. Because of the lower operating temperature, less fuel is required for heating, and refractory-lined combustion chambers are usually not needed. In some cases, it is possible for the catalytic oxidizer to operate without supplemental fuel, except during startup. The primary disadvantages of catalytic oxidizers are the cost of the catalyst and performance problems related to physical and chemical deterioration of the catalyst material. Catalytic oxidizers usually cannot be used effectively on waste gas streams with high concentrations of liquid or solid particles. These particles deposit on the catalyst surface, blocking access for the organic compounds. This is termed fouling. When low concentrations of particles are present, periodically cleaning the catalyst can restore more than 90% of its activity. Certain metals can react or alloy with the catalyst, permanently deactivating it. This is referred to as catalyst poisoning. Some materials, principally sulfur and halogen compounds, have a high adsorptive affinity for some catalytic surfaces, reducing the active sites available to the organic compounds. This is termed masking. High temperatures can also result in catalyst deactivation. Loss of activity because of high temperature is referred to as thermal aging. This results in a rapid loss of catalyst activity and is caused primarily by the sintering of the catalyst support material. Sintering involves the merging of the support material ridges. As this occurs, the catalyst is trapped below the surface of the support material and is no longer available to the organic compounds. Extremely high temperatures can cause volatilization of the catalyst material. Because of fuel costs, most incinerators use heat exchangers to recover some of the heat from the treated gas stream. That heat is usually used to preheat the contaminated gas stream before it enters the incinerator. Two types of heat exchangers are used: recuperators and regenerators. The most common recuperator is the shell and tube heat exchanger. These devices have a shell that encloses numerous small tubes. The contaminated gas stream flows through these tubes, while the treated gas stream flows through the shell across the tubes. Heat from the treated gas stream is transferred through the tubes to the waste gas stream. A regenerator is a set of refractory beds that store heat. Heat recovery is achieved by passing the waste gas stream through a packed ceramic bed at the inlet to the incinerator that was previously heated, with the gases exiting the incinerator. It is common to use at least 3 beds in a regenerative system. One bed is used to preheat the waste gas stream. One bed is used to store heat from the treated gas stream. And one bed is in a purge cycle. The purge cycle is needed to prevent emission spikes each time the gas flow is reversed. A set of gas flow dampers is used to switch the inlet, outlet, and purge gas streams to the appropriate beds. To review, the 3 common types of incinerators used in air pollution control are flares, both ground level and elevated, and thermal oxidizers. This type of incinerator has alternative devices sometimes used, which are process heaters and boilers. The third type of incinerator is catalytic oxidizers. Most incinerator systems preheat the contaminated gas stream with 2 types of heat exchangers. Recuperators, the most common being the shell and tube heat exchanger, and regenerators, usually designed with 3 packed beds to transfer heat. An incinerator's efficiency in destroying a contaminant gas can be affected by the concentration of the organic gas, the ignition temperature, and the residence time or catalyst volume. There are several factors that contribute to the loss of performance in thermal and catalytic oxidizers. These problems include low combustion temperatures, inadequate residence time, inadequate mixing of the gases, burner combustion problems, short-circuiting through the heat exchanger, fouling or plugging of the heat exchanger, generation of additional pollutants in the incinerator, or loss of catalyst activity. The ability to evaluate potential problems during a field inspection will depend on how well the system is instrumented. Most large incineration systems are well instrumented. However, smaller systems may have limited instrumentation. Performance evaluation of these systems will be limited unless measurements of important parameters are made. There should be 2 goals in any field inspection. First is to evaluate the source's compliance with any rule-specific monitoring requirements and with the provisions of the Title V permit. In addition, parameters that influence performance should be evaluated to see if there are shifts from their baseline values that could indicate reduced destruction efficiency. The most direct measure of the performance of an incinerator is the organic vapor concentration in the outlet gas stream, usually measured downstream of the heat exchanger. High outlet concentrations could result from low combustion temperature, reduced residence time, inadequate mixing, reduced catalyst activity, or short-circuiting of emissions through the heat exchanger. If there is a permanently installed analyzer, the adequacy of the data should be checked as part of the overall performance evaluation. This would include an inspection of the condition and integrity of the sampling system and a check of the sample gas flow rate. In addition, the calibration frequencies and procedures in the maintenance records for the instrument should be checked. Calibration should be performed on a daily basis using a calibration gas cylinder that is less than 6 months old and has a pressure of at least 150 psig. If there is no permanently installed analyzer, the concentration measurements will have to be performed with a portable analyzer. However, a dilution probe may be necessary to avoid temperature damage to the instrument. Due to the limited pump capacity of these analyzers, measurements must be made in the portion of the outlet ductwork that is under positive pressure. Both permanently mounted and portable analyzers can provide an accurate indication of the outlet concentration when they are calibrated for the specific compound or compounds present in the gas stream. Often, outlet concentration measurements required by regulation are based on calibrations with a reference gas. The instruments are calibrated using a readily available organic compound such as methane, propane, hexane, or 1,3-butadiene as specified by the applicable regulation. Under these conditions, the instruments will provide a measure of performance relative to a compliance limit expressed in units of the calibration compound or as carbon. The most important operating parameter used to evaluate the performance of a thermal oxidizer is the outlet gas temperature. This is always monitored since it is used to control the fuel flow to the burners. Lower temperature will result in decreased destruction because of the longer reaction time. Also, as the temperature decreases below 1,300 degrees Fahrenheit, equilibrium conditions cause the carbon to be increasingly converted to carbon monoxide, or CO, rather than CO2. Both the inlet and the outlet gas temperatures are used to evaluate the performance of a catalytic oxidizer, since the temperature difference is directly related to the amount of organic vapor being destroyed. Decreases in the temperature difference across the catalyst may occur because there is less organic vapor in the inlet gas stream. This condition could be evaluated using a portable analyzer or a permanently installed lower explosive limit detector if one is available. Decreases in the temperature difference will also occur if there has been a loss of catalyst activity, since less of the organic vapor would be destroyed. If the outlet temperature is being monitored, then records should be examined to detect high temperature excursions, since these could damage the catalyst or downstream heat exchange equipment. The increase in the temperature of the waste gas stream across the heat exchanger provides a useful indication of its physical condition. The accumulation of particulate matter in the heat exchanger reduces transfer efficiency, resulting in increased fuel requirements. Decreased gas flow rates will result in reduced capture of the contaminants at the source, resulting in fugitive emissions. A decrease in the gas flow rate is indicated by decreased fan motor currents and decreased hood static pressure. Increased gas flow rates will shorten the residence times in the incinerator, reducing destruction efficiency. An increase in the gas flow rate is indicated by increased fan motor current and increased hood static pressure. Even though incinerators handle gases that cannot generally be seen, stack opacity is still a useful inspection parameter. Visible emissions are caused by non-combustible particles in the waste gas stream, soot generated by improperly operating burners, and nucleation of pollutants generated in the incinerator. The presence of a soot plume indicates severe burner firing problems. This can lead to fouling of the heat exchanger and, in extreme cases, reduced temperature in the incinerator. A nucleating plume usually indicates the formation of sulfuric or hydrochloric acid vapor in the incinerator. Adjustments or modifications to the burner can reduce sulfuric acid vapor formation. However, these do not work for hydrochloric acid vapor. To determine if an incinerator is operating correctly, field personnel should observe, if possible, the outlet gas stream VOC concentration, either with permanent or portable analyzers, the outlet gas stream temperature for thermal oxidizers, the difference between the inlet and outlet gas stream temperature for catalytic oxidizers, increased gas stream temperature across heat exchangers, decreases and increases in the gas flow rate, and stack opacity. As with any inspection of an air pollution control device, attention must be given to the systems, records and physical condition, and compliance with applicable rules. Incinerators used for air pollution destruction have many safety considerations, including hot surfaces and hot work. Further training and experience will be necessary to complete all field tasks safely.